There are lots of other filters we can apply. In fact, the limit of what kind of filters you can apply is basically only imposed by your imagination, although there are many that are commonplace. We do want to make sure that the filter values all sum to 1, so that if the data are a constant, then the smoothed values will be the same constant. One nice but I think underutilized filter is what I call a tent filter. The filter values go from 0 up to maximum linearly. Then they go back down to 0 linearly. Again, we slide the filter through time, but we make sure that all the windows have all the filter values so we don't get values too close to the edges. We lose half a filter width at the beginning and end of the filter. Here is a tent filter applied to the data we've been looking at. It's a 12-point tent filter, 1-year filter essentially. It's still kind of choppy, but as you can see, the noise in the smoothed values is again considerably less than the noise in the original data. We can choose whatever filter width we want. If we go for a 5-year or 60-point tent filter, we still have some wiggling around because noise goes into the filter. That means some noise is going to come out, but the noise has been greatly reduced. And notice how nice and smooth the smoothed values are. We can go to a 10-point or a 10-year or 120-point tent filter. We get even more noise reduction, and we get a nice smoothed value, which, just like before, looks like it's following pretty much a straight line. If we go to a 20-year or 240-point tent filter, we've got a very nice straight line smoothed value, and we've got tremendous noise reduction. By the way, the tent filter gives a smoothed estimate which isn't as choppy as a boxcar filter. That's because the boxcar filter has those sharp edges. It drops from its regular value right down to 0 outside the window, whereas the tent filter goes to 0 from the middle of the window much more smoothly, and so it gives a smoother smooth. Another smooth that's common and very popular is called a Gaussian filter or a Gaussian smooth. The weight function is a Gaussian function, also known as the normal distribution. Now in this case, we cannot include the entire weight function in any window because the Gaussian function never goes to 0 except when the time offset goes to infinity, so we have to allow for that fact. What I do is I pick a finite window length and define the Gaussian filter values within that window. Then I use weight values, which are just exponential of the time offset squared divided by the time scale squared. Tau in this equation is the time scale, and it's the time scale in terms of time, not in terms of number of data. Then I compute the smoothed values as the sum of weights times data values divided by the sum of weights for when there's data. That ensures that if the data are constant, the smoothed values will be the same constant. Now, because we're not insisting that we have the entire filter within any given window, we can push it all the way to the edges of the data if we like. But we should bear in mind that when we get to the edge of the data, we're only using values that are off to the side of the time at which we're trying to smooth the data. That can lead to some edge effects. Here's the result of a roughly 5-year Gaussian smooth. It's pretty smooth. It's very nice and linear. There's been a great deal of noise reduction. So we've got a very nice smooth fit. However, if we apply that filter to data, which consist of a perfectly straight line with no noise, you can see that at the edge we do have some edge effects. The smoothed values don't keep going at the same trend rate at the edge. They tend to underestimate the trend at the edges of the observed time span. So that's an example of the edge effect you can get with a Gaussian smooth when you push it all the way to the edge of the time span. There are also a bunch of fancy smooths, some really fancy sophisticated methods. These include a spline fit. A spline fit, we fit a piecewise polynomial function, usually a piecewise cubic function, to slices of the time slices of the data. But where the time slices meet at those borders, the boundaries between spans, we ensure that the spline fit will match up nicely. The boundaries between spans are called knots. There are also quite a few Fourier filters. We'll discuss those a little bit when we get into Fourier analysis. And there's something very sophisticated called singular spectrum analysis. We'll discuss that a little bit later as well. But I'd like to focus on my favorite smoothing method. It's called a low-S smooth, which stands for locally weighted scatterplot smoothing. It too uses a sliding window on the data. Within the sliding window, what we do is a polynomial regression. Then we take the value of the polynomial fit we get at the moment we're interested in as the estimated smoothed value. The polynomial order is usually kept very low. In fact, our implementation of a low-S smooth defaults to a linear or degree 1 polynomial, but I prefer to use a quadratic or degree 2 polynomial. Within the sliding window, the fit is done by weighted least squares, with a weight function designed to emphasize what's in the middle of the window, actually to emphasize what's at the moment of time for which we're trying to estimate a smooth, and we downweight what's at the edges. The usual weighting function is called the tricube function, and here is what it looks like. After the first pass, we can add on to the low-S smooth in an especially sometimes very useful way. After the first pass, we've got a smoothed estimate. Then we can subtract the smoothed estimate from the data to get residuals. Then the residuals can be scanned to see what data points are way outside the smooth, the points that might be called outliers. Then we can downweight the outliers and repeat the process. If we do that, we'll get a new low-S smooth. Then we can go through that whole thing again, subtract it from the data to get residuals and look at those for what's an outlier and what we might want to downweight for further iterations of the low-S smooth. Now, I've written my own sort of low-S routine and I've made some modifications. So I wrote my own modified low-S smooth program. I use a different weighting function. And instead of a quadratic fit, I use a modified quadratic fit because when you use a quadratic fit in a low-S smooth, it can sometimes exaggerate curvature at the very end points of the time span. So I created a modified quadratic which prevents too much curvature happening at the edges. I also take the trouble within my own program to compute the uncertainty of the smoothed value. That's something you can do with an ordinary smooth, an ordinary low-S smooth, in fact with just about any smooth. But most smoothing programs don't bother to compute it for you, so I wrote my own program to compute it for me. Also, I compute the slope of the smoothed fit, so I can use it to estimate what the slope of the signal is at various points in time, which sometimes is very important and very useful. I suggest you use ordinary low-S, whatever is included in your software. They're all good, and if you use the ordinary low-S that is included in your software, you'll get used to it. You'll learn its ins and outs, its strengths and weaknesses, and you'll get better and better at it. Here's the result of applying a low-S smooth that operates with a time scale of about a year on our original data. Now, usually when you run a low-S smooth, you don't specify your time scale in terms of the amount of time in the window. Instead, you specify it in terms of the number of data points to be included in the window. Often that's given in terms of the fraction of the total data that is included in the window. But it turns out that for this particular fit, the window width gives you something that's roughly comparable to doing a moving average or boxcar filter on a time scale of 1 year. If I up the time scale to 5 years, it looks like this, getting very smooth, very good noise reduction, and the signal is looking still like a straight line with some wiggles. A low-S smooth, like every smoothing method and every filtering method, there's going to be noise going in, so there's going to be noise coming out. If I up the time scale to 10 years, I'm getting a very smooth and nearly nicely straight line, which suggests to us strongly that the underlying signal is actually a straight line. If I do that and I plot what is the uncertainty range, because my program that I used actually computes the uncertainty range for me, we can see that this is a very nice, tight, smooth fit. Now, the uncertainty range is the uncertainty of the smoothed value or the underlying signal, if we've got the signal right. It's not the uncertainty in the data because the data includes all that noise, which has a lot of variation to it. But it does give us an idea of what the signal is and how uncertain the underlying signal is. That only applies if we've got the underlying signal right. If we have smoothed it too much so that we're wiping out part of the signal that happens on fast timescales, then our estimate of its uncertainty isn't going to be realistic. In this case, the data that I created actually did follow a straight line plus random noise. I wonder how well this particular low-S smooth matches the true underlying signal. Well, in fact, it matches it very well. In fact, at every moment of time, the true signal is within our estimated range. And once again, that's not always going to be the case. This is about a 95% confidence range. Well, remember that you expect things to stray outside the 95% confidence range about 5% of the time. So cases like this where the true signal is actually within the confidence interval at all times are actually pretty rare, but we got lucky this time. Also, this is an exceptional case in another way, namely that we know what the true signal is. In most cases, we aren't working with artificial data. We're working with data where we don't know what the true signal is. That's what we're trying to find out.